Hello guys, welcome to the Innovation Lab. In this video, we're going to conduct a test to know if we can connect the outputs of two non-input output isolated DC to DC boost converters in series. And the goal for doing something like this will be to know if we can possibly increase or double the output voltage or output power of our DC to DC boost converter system by connecting these converters in series. Alright guys, our overall goal for these converter videos is really to find affordable solutions that will address some of the converter limitations that we're finding with respect to our individual projects, be it battery charging or different kinds of things that you're doing. I know that some of us have kind of a need for lower voltage but high current applications, and some of us may have a need for higher voltage, lower current applications. So in a nutshell, the focus of this specific video is to know if we can provide a solution to those of us who have a need for high voltage DC applications. All right. For those of us who still have a need for converters that can provide high output currents, I know that some of you guys have reached out and said you need converters that can do upwards of 50 amps to 100 amps or more. And that was what inspired the video that we made to see if we can connect the boost converters in parallel. And that did not go so well. And that also inspired us to try to build our own DC to DC boost converter. And we're thinking of actually making it a massive build, as you guys can see on this heatsink here. Because one of the problems I'm seeing with the designs that you can get online is that there is this need to make everything super compact these days. And then, of course, something has to give. So we're trying to remove that concern by making everything bigger. So the inductors are going to be huge. The heat sinks are going to be huge. So our goal is to use as many MOSFETs as we can, just to increase the reliability and the function and the output current going out of these converters. So if you like to see all of that, if you would like to know what we're doing, get constant updates on that, subscribe to the Innovation Lab. Alright guys, we decided to make this video because after the video that we made to experiment on connecting two of these boost converters in parallel, a lot of you guys have been making the request and asking us to make a follow-on video to show if it will be possible to connect these boost converters in series. For something like this, my initial response was that these converters are non-input output isolated. So what that means is that the input ground and the output ground is tied together, and that makes it almost impossible to connect the outputs in series, because when you do that, you're going to be shorting one of the converters, and that will not be good. So my initial response was that no, it cannot be done, it's not possible, we're not going to make the video. But then after I gave it some thought, then I realized that I actually may have done something like that in the past. So that's why we decided to make this video to show you guys that it is possible. There is a way you can do it. It's not going to be a straightforward process. It's going to be a little bit an intricate process, and we're going to show you guys the different methods that you can use to accomplish this function. Alright guys, let's get into it. Alright guys, so when I say that there is a way to do it, so the summary of it all is that what you're going to need to do is to drive each individual DC to DC boost converter with an isolated power supply or power source. So, and I'm going to show you guys three different methods that you can use to provide that isolated power source to each converter. So the first method is to use two individual battery systems, and one battery system will drive each converter. The second method will be to use servo power supplies, individual output isolated servo power supplies. And those servo power supplies, the outputs have to be isolated from the chassis grounding of each supply, as we showed in our last video. And finally, the last method that we're going to show in this video will be the transformer method. So in this process, we're going to have transformers, individual transformers with primary and secondary windings that are isolated from each other. And we're going to rectify the output of the secondary side of the transformer. So the goal will be to use each individual transformer with a rectified output to drive each DC to DC boost converter. Actually, there is also a way that you can do it using one single transformer, but with center tap configuration. So the only thing is that you need to make sure that the center tap transformer, the windings are not tied to each other. They're actually isolated from each other. And I'm going to show you all of that in this video. All right. Before we get started, I would like to take the time to thank you guys for all your support. Thank you guys for subscribing to our channel, for giving us wonderful ideas and providing all the inspiration that we need. Making these videos are very time consuming and it takes a lot of effort, and it wouldn't have been possible for us to go through all of this if it wasn't for all your support. Also, I want to thank my very close friends for all their support and inspiration and teaching me things that I didn't know, from YouTube to video recording to providing some of the things that I needed. I have a friend that actually he's very good with cameras and lighting, and he showed me a lot of things that I didn't know. I really appreciate him. If you're watching this video, I want you to know that I appreciate all your support and I thank you for that. Also, I want to say a big thank you to my other friends that have in multiple occasions donated some used electronics or old electronics like these transformers here. They found them and donated them to the Innovation Lab, and that's just an example of multiple things they have given to us. If you're watching this video, I want you guys to know that we appreciate all your support and we thank you for all of that. Alright guys, the plan is to move things around a little bit to keep the video fun and interesting, and I believe that we have already covered the introduction. Now we are going to present the different sections to you guys, and I hope that you guys find the video interesting. Alright my friends, if you like the video, don't forget to give it a thumbs up. Don't forget to save it for something you can use as a future reference. Alright guys, and now let's get started. Alright guys, as you can see here, our setup is complete. We have connected the batteries, and we have the first battery going to the DC to DC boost converter here, and we have the second battery here going to the second DC to DC boost converter. And as you guys can see, these systems are totally isolated. So we have this battery, the ground is here. We have the second battery, the ground is here, and we have absolutely no link in the grounds. So the first thing we did was to adjust the output current to the maximum point for the first converter, and we did the same thing for the second converter. And the reason for this is that we want some level of uniformity in their performance. So, and how you do that is, as you guys can see the arrow here. So if you go counterclockwise in the direction of the arrow, you're going to be dropping the output current level. So you want to go counterclockwise until you hear some clicks on the potentiometer. That's when you know that you have gotten to the maximum point. And again, you do it on both potentiometers. And the second thing I did was to adjust the output of each converter. So for the purpose of the voltage test, I set each output to 60 volts, as you guys can see here. And I had the second converter disconnected as well, just to be safe. I don't know that it matters, but just to be safe. So I had disconnected it first, and I went ahead and I adjusted the output as well to 60 volts. So they are not exactly at the same voltage level. Again, I don't think it matters. So this one is at 60.1 and this guy is at 60.5. And let's see what we're getting on the output. And there you have it, my friends. We have 120.6, which is exactly acting as you would expect. You have two voltage sources connected in series, the same response you get when you connect batteries in series. You have 60.2, 60.5, and when you look here, we're averaging about 120.7. All right, guys, it looks like this is working. The voltage test is working, but we are not out of the woods yet because we have to put a load on this to see how it's going to respond. All right, guys, let's get to that. Alright guys, as you can see here, the setup is complete. But before we begin, let's go ahead and review the safety of our setup because high voltage is involved. So we want to make sure that we are being safe, especially if you guys would like to do something like this in the future. We want to make sure that you're doing it safely and you're not going to have any issues. So going from the left here, we have our lithium phosphate battery pack, of course, and inside the battery pack we have our BMS that protects each battery from over discharging. If each battery is running low to a point, it's going to cut off. One thing I'd like to mention here is that if you guys decide to try the battery method, there is kind of a risk here because as you guys can see right now, this is kind of two individual systems that we're tying their outputs together to give us the resultant output voltage that we need. So as you guys can see here, we have 60 volts coming from we can call them system A, and we have 60 volts coming from system B. When we connect them in series, we get our 120 volts. But now the disadvantage of the battery system is that if one battery runs down before the next one, so you will automatically be losing 60 volts on one of the systems, and your resultant output voltage will drop down to 60 volts. So if you really want to try this, what I would recommend is that you build in a voltage monitoring circuit. Either you build it at this stage to monitor each of the battery levels and say if one has dropped out, kill the entire system, or you can build it at the output stage and say if our output drops below 120 volts, kill the entire system. It might be a good idea to add a switch at the output to kind of control the whole system. So the advantage that we have here of being able to isolate each battery system, also there is a safety disadvantage, and we have to make sure that we talk about that. All right, So going to our DC to DC boost converters, we have our input fuses here that will protect the system from overloads, and we have the same for the next converter, and we have our under voltage lockout protection that's going to protect the system from under voltage, and we have an overcurrent protection also built into this DC to DC boost converters. This is the reason why I love using them, because they are not just cheap, but they also come with some good functions. All right, and we're going to be monitoring our voltages using these power monitors to kind of tell us the behavior of each DC to DC boost converter, you know, how much they're contributing to the test, voltage, output current, output power. We're going to be able to get all that information from the power monitors. All right, so kind of the big feature that I added to our test setup, and I showed this in my last video and it's going to be in our videos going forward, is this load control module here. And why this is a safety device is that it allows us to slowly ramp up the power that we're going to be delivering to our load, the voltage and current going to our load, so that way we're not going to slam a whole lot of load onto the system and maybe damage a converter, as you guys saw in one of our videos. And so that will be very helpful. So going from there, we have our circuit breaker that we're going to be using to bring in the load when, you know, we are ready to go. And for the loads, given that we are testing a high voltage system, so I wanted to add more resistance in the path of the load to make sure we don't overload the system. So what we have here is our 20 ohm 500 watts power resistor network, and going from there we have our, this is really a network of two 48 volts 1000 watt heaters that we connected in series to allow us to test high voltage power systems. All right guys, so that's really it for the safety review and kind of an overview of what we have here in this test setup. One last thing that I missed is that we also added this portable fan here to allow us to keep this load control module cool, because if we keep it cool, we're not going to have any power drifts because of the shift in drain to source resistance of the MOSFETs that we're using here. But then that's a story for another video. Alright guys, what we're going to do for the battery method testing is really very simple. We have our 12 volt battery systems here, and they come into the DC to DC boost converters. From there we boost them up to 60 volts on each system, and the systems are tied in series to give us the 120 volts DC that we have here. And here, as you guys can see, we have our load. And now what we're going to do is, when we start the test, first of all, we're going to make sure we turn on the fan and we close the circuit breaker, and we slowly, using the load control module, begin to apply the load. So at 12 volts, I've done my calculations on these converters. At 12 volts, they should really be able to give us about somewhere between 360 watts or so going into the converter, but we're going to play it safe. So we're going to try to push it up to about 500 watts. All right.
Tell me what you're thinking, give me what you're drinking. Tell me what you're thinking, give me what you're drinking. You and me, we got something special, baby, you and me. You and me, I can think this was never meant to happen, you and me. You and me, I can't help it. Tell me what you're thinking, give me what you're drinking. Tell me what you're thinking, give me what you're drinking. You and me, we got something special, baby. You and me, you and me. I can think this was never meant to happen. You and me, you and me. I can't help it. I can't help it, baby. I can't help it. I can't help it, baby.
Alright guys, as you guys can see here, our setup for the second phase of the testing is complete, and I guess that we can call this the isolated SMPS method. And for that, we're going to be using the same server power supplies that we used in our previous videos. So all we had to do was to pull them out of the power rack that we built a while ago, and these server power supplies are already pre-configured. So basically that makes it easier for us to just use it in this application. And we have the first server power supply connected to our main supply, and it goes to the first DC to DC boost converter, positive and negative. And we have a second server power supply. The same thing applies, positive and negative, and it goes to our second DC to DC boost converter here. And each of these server power supplies can deliver up to 750 watts of output power. So one thing I'd like to mention, if you haven't seen our other videos where we showed how to isolate the output of these server power supplies, normally the negative bus of the power supply is tied to the chassis ground, and I believe is connected to the earth ground. So the only thing you're going to have to do is to make sure that the negative terminal of each of these server power supplies are isolated from the chassis ground, because if you don't do that, everything we're doing here is not going to work, because it will be as if the two grounds are tied together when you connect them in the system, and it's not going to work. And we actually showed how to do this in our power rack video, and I will be adding the link to that video in the description for this one. Alright guys, that's all you have to do. So server power supply A will supply power to the first DC to DC boost converter, and server power supply B will supply power to the second DC to DC boost converter, and the outputs are tied in series after our digital power monitor, and that allows us to see what's going on. Alright guys, let's go ahead and power up the system and start conducting some load tests on it. Alright guys, I had to modify the setup a little bit going forward because I ran into an issue on the setup. I mistakenly damaged the load control module because I was trying to basically put more load on the system by removing the resistor stack here and just putting on the heaters directly to the system. And by doing that, I kind of made a mistake. I think I might have went too fast with adjustments and shifted all the load to the control module, and they damaged the control module. And secondly, as you guys saw earlier, I was using 2 of these digital power monitors, and the plan was to connect each monitor to the output of each DC to DC boost converter. That way we can see what's coming out of that converter going to the load. But what I realized was that I don't think that these digital power monitors perform well when you have the outputs connected in series before going to a load. So it tends to kind of confuse the power monitor because I wasn't convinced that the measurements I was getting was accurate. So what we have here now is that we are basically kind of connecting the converters in series first. Then we are sending all of that through the digital power monitor. And from there, we go to our load. And for the load, also, we decided to change it to, instead of using the heater and the resistor stack, so we decided to change it to this high voltage AC load box that I made a while ago. And I made this load box for testing my inverters. So this is supposed to be an AC load. But what I realized a while ago is that even though especially for incandescent light bulbs and some LEDs, even though they are rated for AC application and at 60 Hertz, you can also drive them with DC, but this is not something I would recommend. I am doing this because I am just using them as dummy loads, so I don't recommend that you guys drive this something like this with high voltage DC because they will end up damaging the light bulbs and also will consume more power for you. So I'm only using this here for educational purposes, just for testing this system. All we need is a way to put a load on this system. That's it. So I do not recommend that you guys do this at home. We're just doing this just as a way to put a load on this system. So as you guys can see, are the multiple switches. So we're going to be bringing the load in steps. So that could also be an advantage. So this is an 80 watt line. And here we're going to be adding 200 watts, 200 watts, 200 watts, and 200 watts. Hopefully we get to about 1,000 watts or so. Let's see if we can make it happen. So these guys here are not all the way in, so they may not, we'll bring them in as if we have the need. All right, guys, that's it. And so we're taking our time to make sure that you guys understand everything we're doing. If you have a question, leave us a comment. We will be happy to answer that. All right, so let's go ahead and turn on the power and see how the SMPS is going to perform in these test conditions. All right, guys, we have powered on the system and it's up and running, and the humming noise that you guys are hearing is coming from the server power supplies over here. All right, and they're working really well. So one thing that I missed to mention earlier was that I added 2 DMMs to the setup, and the green DMM is used to monitor the output voltage coming out of the first DC to DC boost converter, and the fluke DMM is used to monitor the second DC to DC boost converter, so you guys can see it. So we have 60 volts and 60 volts. And after we combine them in series, now we are monitoring them at the power monitor. You can see here 120 volts, and that's what's going to go to our load. All right, let's begin. We close our breaker. All right, I'll do that again so you guys can see it come up. Breaker off. Wonderful. All right, so what we have there right now, my digital power monitor is showing us 50 watts or 51.9 watts on that line. So let's go ahead and start stepping up the load, and the output is holding steady at 120 volts. We have an output current of 0.43 amps. So let's bring in the first channel. All right, so now what do we have? We have 196 watts, and the output voltage is still holding steady at 120 volts. So one thing I forgot to do was to turn on this fan just to help cool the system. Let's go ahead and do that. Alright, at this point it's going to get noisy, so I'm just going to go through the load stepping. Alright. Something was off on that channel. So right now we are at 388 watts. At 120 volts, output current is at 3.21. Alright guys, we were able to bring in about 4 channels. We're just trying to play safe here, and with that we are measuring about 584 watts. As you guys can see, the output voltage is holding steady. This is quite impressive, and we have an output current of 4.85 amps. And so if you look at the output of each converter, we're getting 58.9 from the first one and 60.3 on the second one. And yeah, this is quite impressive. They're holding really well. Yeah, maybe on the transformer test we can try to push it a little more, see if we can get to 1,000 watts, because we don't want to damage the converters at this point. We still have one more test to go. Yeah, this is quite impressive. I am glad that this is actually working. All right. Alright guys, unfortunately I have to end the video here because I made a mistake at the last load step that I did. I forgot to account for the input voltage level that was required for that level of testing. So these server power supplies can only deliver about 12 volts. So if you do the math, 12 volts input going to each converter, and the input current limit of about somewhere between 30 to 40 amps. So we shouldn't really be pushing these two converters more than like 700 watts of output power. So during the testing, because everything was going so well, I got carried away and I put more load on the system, and I ended up damaging the system. So what you're looking at here is more than 1,000 watts of load. And as you guys saw, when we turned everything on, we were getting about close to 950 watts of output load on the system. But then it damaged this converter here, I am thinking that it could be the drive MOSFET. That's usually the thing that gets damaged the most. So I'm going to try to repair that by replacing the MOSFET. And what I intend to do is to make a follow-on video to show you guys the transformer method, because what I saw here was quite amazing. Even with all the load that we're putting on the system, the output regulation was wonderful. Yeah, so a lot of you guys out there that need maybe high voltage systems for charging batteries or doing all kinds of things, I think this could be something that could work, but I'm not going to make that recommendation yet until I conduct more testing on this system and possibly find a way to run it for a long time to make sure that these converters will hold up. Doing a short duration test is one thing, but running the system for a while is another thing. So I'm not going to tell you guys to go out there and do this until I mean, if you guys want to do it, you can do it. I don't tell you what to do, but for me to make a strong recommendation and say this is really good, I'm going to have to conduct a follow-on test on this, and I put more load on it. So hopefully with the transformers, with the rectified output, my goal is that we should be able to get close to 20 volts or more at the input of each converter, so that should give us more delivered power at the output. All right, and maybe in the future, if we can find a way to double these power supplies, maybe we can put 24 volts going into each converter, then we can kind of show you guys what the performance will be. All right guys, again, I am quite impressed with how the output voltage regulation held up under load. Yeah, so this is quite impressive, and I'm looking forward to the next testing on this guy. All right, my friends, if you like videos like this, all our videos are pretty much hands-on. You guys get to see what we're doing. And as you guys have seen in this one, we are not above mistakes. We make mistakes, and we kind of had to live with the consequences. And so if you guys like videos like this, don't forget to subscribe to the Innovation Lab. And if you found this video useful, just give it a thumbs up. It helps us a lot with the YouTube algorithm. And also leave us a comment. Go ahead and leave a comment. The only thing I ask is that you guys leave us, keep your comments respectful, constructive. And if you saw something we did wrong, just tell us what we did wrong. Tell us what we did right, what you liked about the video. All right, guys, that's it for this video, and I will see you guys in the next one.